Measurement of electrical mobilities, which are also known as ionic mobilities. So ionic mobilities can be measured by a moving boundary method, which is shown in this figure, which is having a solution of KCl, which is placed over a solution of cadmium chloride in an electrolysis tube of cross-sectional area A. So for this method, the solutions used must have an ion in common. When the current flows, the potassium ions migrate upward to the negative electrode, as do the cadmium ions also. So here, due to the electric field, potassium ions are moving towards this negative electrode. Due to the change in the concentration, the cadmium ions will also move towards this direction. As a result, the boundary between these two solutions will be moved towards the negative electrode, and the boundary can be observed clearly using a refractometer, as the two solutions have different refractive index. For this experiment to work, the lower solution must have lower conductivity, as the mobility is directly related to the conductivity. So the mobility of the lower solution must be lower as compared to the upper solution. As in this case, the electric mobility of the cadmium solution is lower than the potassium, which is the upper solution. The speed of the potassium ions migration is determined by the movement of this boundary with respect to time, and the movement of this boundary can be easily measured using the refractometer. Once the drift speed is known, the mobility of the potassium ions can be measured by equation 2. Here E is the electric field that have been applied between these two electrodes, and this time T is the time required to boundary to move towards this direction. As we know that the conductivity equal to the current density over the applied field. So by comparing equation 1, 2 and 3, we can write the ionic mobility of the potassium ions as, so here A is the cross-sectional area that is expressed when the potential or the field is expressed in terms of current. Here one thing is observed, that this amount is equal to the charge that flows, and it can be measured experimentally using a coulometer. Here we have an example for sodium chloride in aqueous solution at 25 degrees centigrade and 1 atmospheric pressure. So from this graph we can see that the concentration versus the ionic mobility plot is given here, in which the mobility of the chloride ions is higher than the sodium ions, whereas we can see that as the concentration is decreasing to infinite dilution, the electrical mobilities are increasing exponentially. So using the plot given here, we can measure the experimental electrical mobility or ionic mobility that is extrapolated to the infinite dilution for ions in water at 25 degrees centigrade. So let's see some examples. So here we have examples of experimental electrical mobilities that are extrapolated to infinite dilution for ions in water at 25 degrees centigrade and 1 atmospheric pressure. So here we can see that the ionic mobilities of the hydronium and hydroxyl ions are far higher than the other values. And it is observed that for small inorganic ions, the um, mobilities at infinite dilution are usually observed between the range of 40 to 80 into 10 to the power minus 5 centimeters square per volt per second. However, the mobility of the hydronium and hydroxyl ions show abnormally high mobilities. These high mobilities are due to the special jumping mechanism that operates in addition to the usual motion through the solvent. A portion from so a proton from an hydronium ion can jump to a neighboring water molecule, a process that has same effect that the hydronium ion is moving through the solution like this, but actually the proton is jumping from one water to other water molecule. But overall it seems to be that the hydronium ions are moving. Similarly, for hydroxyl ion, the high mobility is due to the transfer of proton from water molecule to the hydroxyl ion. So we can draw this mechanism as here we have one hydroxyl ion. So a proton from other water molecule will be transferred to this hydroxyl ion. So we have this hydroxyl ion converted to a water molecule, and this one is changed to hydroxyl ion. So this mechanism is also the transfer of proton from one water molecule to other hydroxyl ion. So this mechanism also observed to be the movement of the hydroxyl ion through the solution. So due to these movements or the transfer of protons from one ionic species to the neutral species, or the from neutral to ionic species, is the reason for the higher mobilities for hydroxyl and hydronium ions. Experimentally, ionic mobilities at infinite dilution are measured by usually theoretical estimation. At extremely high dilution, inter-ionic forces are negligible, so the only electric force an ion experience is due to the applied electric field. So here the inter-ionic forces are negligible, so the only force that is acting on it, the electric field and the frictional force. When the electric field and frictional force are equal, or when they are balanced, the B ion will move with terminal speed, that is the drift speed at infinite dilution. So here we have electric field on ion B that is equal to this term, and the frictional force is equal to the frictional coefficient and the terminal speed. When the frictional force and the electric field are balanced, so these two forces are equal, and we can write the terminal speed, that is the drift speed at infinite dilution, is equal to the over frictional coefficient. So the infinite dilution mobility is then equal to the terminal speed over the electric field. So by expressing the value of terminal speed, we will have an expression for the ionic mobility in at infinite dilution in terms of the frictional coefficient, which can be given as six pi eta RB, where eta is the viscosity of the solution and RB is hydrodynamic radius, as we consider that the solvated species, for example, if we have sodium ion which is surrounded by water molecules, make a solvated species as spherical. So this equation attributes the differences in infinite dilution mobilities of ions entirely to the differences in their charges and radii. Of course, this equation can be used for the hydronium or hydroxyl ion. This cannot be used for this because here we need to use the hydrated species or the solvated species, showing the spherical geometry. So indirectly using this equation by measuring the mobility of ions at infinite dilution, we can measure the hydrodynamic radii of the solvated species.